Yeah. Good evening, everyone. So what we discussed in the last class, tell me.
Calculation of energy.
So we have completed till Bohr's atomic model with its limitation, okay, and all the model questions related to Bohr's atomic model, right now? Yeah. So now we will be discussing about the de Broglie's hypothesis. Okay, do you remember all these things we have discussed? Lyman series, Boltzmann series, spectral number of spectral lines possible. Okay, what is the formula given? When an electron is falling from nth orbit to any of the lower level, the number of spectral lines possible will be equals to half into n2 minus n1 into n2 minus n1 plus 1. Okay, so this will be the formula you should use for finding number of spectral lines possible. Okay, after that I have given Rydberg's equation and all. Okay, so now look at this. Look at this. What we are going to study today? De Broglie's concept of dual nature of matter. Okay, so from Planck's quantum theory, what we have? Energy is considered as energy equals to, let me change the pens. Okay, yeah, so energy E is equals to h nu. This is what comes from Planck's quantum theory, and from classical mechanics, from Einstein's theory, we have E equals to mc square. Okay, we can write like this. Both are energies only now. So now here, considering both of them are as equal, so what we can get? E is equals to h nu, which is equals to mc square. So h nu is nothing but hc by lambda, which is equals to mc square. So this c and c from here are removed. Okay, so I can write lambda equals to h by mc. Okay, mc. This c represents here speed of light. Okay, so speed of light. Speed of light, where h is Planck's constant and m is mass here. Okay, so now I can replace c with microscopic particle, velocity of a particle now. So therefore I can get h equals to lambda equals to h by mv. Okay, so what is here v? Here v represents velocity of that microscopic particle we are taking. Okay, and mass here, m is a mass of that particle, and h represents Planck's constant. Okay, what is the value? H equals to 6.6 into 10 power minus 34 joule second. Okay, lambda is wavelength here. Okay, this is how we can calculate de Broglie wavelength. Okay, so write this final formula, h lambda equals h by mv. Yeah, we will do some questions related to that. Yeah, so now here we can also relate wavelength to the kinetic energy. Okay, how can we relate that? See, kinetic energy means half mv square we can write. So from this I just want to convert here mv we have, here also I just wanted to modify equation as per that. So multiply both sides with mass, so that kinetic energy k multiplied with mass m is equals to half m square v square, that is nothing but mv whole square, here 1 by 2 as it is. Okay, next mv means what? It's a momentum here. Okay, so I can write mv square is equals to 2km. Okay, k means kinetic energy, m is mass here. Okay, I want mv means root over 2km. Okay, yeah, so write this value in this first equation. You can get h by mv means root over 2km. 2km. So this is a relation between wavelength and kinetic energy of that particle. Okay, like this you can make one more formula. Yeah, these formulas are useful while doing the numericals now. Okay, now I will show you few numericals related to this particular topic. Okay, so now first of all, look at this question. Calculate the wavelength of electron revolving in the first orbit of hydrogen atom, they will be asking. Okay, so there are two ways I can give you for solving this particular question. So first one is lambda equals to h by mv. What they are asking? Wavelength they are asking. Okay, so from Bohr's atomic model, what we can say? mvr equals to angular momentum equals mvr equals to nh by 2 pi. Okay, this is angular momentum quantization condition. Okay, from this I can write mv equals to nh by 2 pi r. Okay, so from here also mv equals to h by lambda I can write. Right now both are mv both are equal. So from this what we can say, mv equals to h by lambda, which is equals to n by 2 pi nh by 2 pi r. Okay, h is removed, so we got n lambda equals to, I am sending this here, n lambda equals to here 2 pi r for nth orbit rn. Okay, h lambda, n lambda equals to h by h like 2 pi rn. So this is also de Broglie's equation. Okay, so from this what they are saying, what is the orbit number they are saying? First orbit, lambda n equals to 1, so lambda we need to find 2 pi and r1. So r1 of hydrogen atom is how much? Radius of first Bohr orbit. It means r1 of what is the formula for radius? 0.529 n square by z. So what is the n value they mentioned? 1. So n is 1. Atomic number of hydrogen also 1. 0.529 angstroms. So this is r1. So right here lambda equals to 2 into pi means 3.14 into this one is 0.529. Okay, so yeah, but this is the simplest way you can solve it. Okay, so that you will get 3.34 angstroms approximate value. Okay, this will be your answer. Okay, if they ask in meters, you can write 3.34 into 10 power minus 10 meters. Okay, so this will be the value of lambda. Is this clear or not? Yeah, so this is the best way or simple way you can solve. Okay, you can make your notes out of it. Okay, so if you want one more method, you can also solve using this method also. Lambda equals to, what is the formula we have? H by mv we have. So v means what? Velocity. So velocity of electron moving in the first orbit. So what is the formula for velocity? 2.18 into 10 power 6 z by n meter per second. Okay, so from this velocity of first Bohr orbit, electron in the first Bohr orbit can be 2.18 into 10 power 6, z is atomic number is 1 and n is also 1. So meter per second you will get. This is the value you will get for velocity of electron revolving the first. What is the mass of electron? 9.11 into 10 power minus 34 joule second. Okay, sorry, minus 31 joule per kg. This is mass of electron now, minus 31 kg. Okay, so now what I want? Lambda equals to h by mv. So lambda means, what is the h value here? 6.6 into 10 power minus 34 joule second by mass 9.11 into 10 power minus 31 into velocity is 2.18 into 2.18 into 10 power 6 meter per second. So by simplifying this you will get same answer like this. Okay, both ways are correct only here. Okay, yeah. Next, done? Have you written? Finish that? Yeah. next question, write a question, find the wavelength lambda of a cricket ball of mass 20 grams moving with a velocity of 100 meter per second.
Lambda is equal to
Yeah.
h by 2 pi. mv, sorry. mv. H is equal to 6.
So how can you do this? Lambda equals to h by mv. So 6.6 minus 34 joule second into mass is how much? So 20 gram they mention na. See, joule you can write it as kg meter square per second square. Okay, in the place of joules you can replace with this. Okay, so here we have kg, here we have grams right now. So you can convert this into 10 power minus 3 kg, 20 into 10 power minus 3 kg. Okay, now you can remove kg. Okay, and velocity given as 100 meter per second. Okay, yeah. So this units you remove first, meter and square, this seconds you can have removed. Okay, next what you can do? Yeah, see, here we have 20 and here we have 100 into 10 power minus 3. So 10 power plus 3 into 10 power minus 3. So you can remove these zeros here completely. So what you have here? 2 1s are 2, 3, 3. So 3.3 into 10 power minus 34 meters we got. So this is a lambda value which is very small here. You can also write this value as 3.3 into 10 power minus 24 angstroms. Okay, so this value also even very small value. Okay, angstrom itself is a small unit. Okay, again it is multiplied with 10 power minus 24. The value is almost like a negligible amount. Okay, that's what we have discussed. De Broglie's hypothesis, like de Broglie wave equation, not applicable in case of macroscopic particle. It is applicable only for micro, small particles only. Therefore, see, this cricket ball is a macroscopic, large particle, large substance like mass. It has bigger mass, 20 grams. So it's a macroscopic substance which is having very low wavelength. That value is almost negligible. Okay, you can write the statement. This de Broglie wave equation applicable only for microscopic particles.
Sir, whenever giving grams, we should convert it to kg.
Yeah. Over. Next, we'll study this Heisenberg's uncertainty principle. So what it says, Heisenberg's uncertainty principle. See, it is impossible to measure simultaneously the position and momentum of a small particle with absolute accuracy. It means if a small particle is there which is under movement, okay, which is under motion, so we cannot find its exact position and its exact momentum simultaneously. Okay, it means if we try to find, there will be some error in the calculation or in the measurement. So that error in the position, I am writing it as delta x. Delta x represents what? Error in position, and delta p represents error in momentum. So the error of the product of error in position and error in momentum will be either equal or greater than h by 4 pi. Okay, the value of the error will be either equal or greater than h by 4 pi times. Okay, so this is the like HUP, Heisenberg's uncertainty principle. Okay, so you can write P means it's a momentum now. So momentum means mass into velocity. So delta P means I can write m into delta V. Okay, so you can write change in position into change in momentum we have now. So I am replacing that with mass into change in velocity h by 4 pi we can write. So from this delta x into delta v h by 4 pi m we can write right now. So while doing the numericals, you just consider delta x into delta p h by 4 pi, like that you can consider and you can simplify the solution, okay, problem whatever they mention. Okay, so this is about what HUP here, Heisenberg's uncertainty principle. Now let us see one or two questions on this. See, the uncertainty in the position and velocity of a moving particle are this much. Position is given and velocity also mentioned. The mass of particle is how much they are asking. Okay, so now what we can do? See, delta x delta p equals to greater than or equals to h by 4 pi I can write. Okay, okay, so here momentum is there now, so they mentioned velocity, so you can write delta x into delta v equals to h by 4 pi m. Okay, what is the velocity position, the uncertainty in position 10 power minus 10 meters, and velocity 6.6 into 6.626 into 10 by pi into 10 power minus 24. Okay, then next so here what is the h value given? See, 6.626 into 10 power minus 34 joules. Again next joule seconds. Okay, and 4 here and pi. Okay, pi into mass we need to find that value. Okay, so pi, remove the pi, and next here minus 10 power 10 minus 10 power 24, that is minus 10 power 34. This side also we have. Okay, so meter, and here also we have meter, so this will be removed. So finally we will be getting here just kg will be remained here. Okay, so next what are the other units? See, 6.626 it can be removed. Okay, so mass is equals to 1 by 4 we have, so that is 0.25 kg. So we have 0.25 kg here. So first option will be your answer for this question. Is that clear? Yeah. Let us move on for one more question here. Yeah, look at this. The uncertainty in the velocities of two particles A, B are given like this. The mass of B is 5 times the mass of A. The ratio of uncertainties in their positions is. So tell me, how can we do this? Just try that from your side. Yeah. So how do we do this? The uncertainty in the velocities of two particles A, B are given. Okay. So it means delta V is given and delta X they are asking. Very easy. So delta X into delta V, and masses are also given now. So it means you can take into M also h by 4 pi. Okay, so like this we are writing now. So now use this equation and you can solve that. See, I can write, this is for A, okay, and I can write delta XB, delta VB, MB, so h by 4 pi. So which can be removed here. Okay, so we have delta X A, okay,
0.
what they are asking us,
Position.
velocities are given. So delta xa by delta xb they are asking. So remaining terms you can send that side to the equal side. So it becomes mb into vb by velocity of b by ma into velocity, error in velocity of a. Okay. So what they mentioned here, mass of b. So what is the mass of B mentioned here? The mass of B is 5 times the mass of A. So mass of B, here I can write 5 times mass of A, and here mass of A we already have here. Okay. What about velocity of A given? 0.05. And what is the velocity of B given? 0.02. So you can remove these two things. Okay, and next, okay, next what we have here, so this will be how many times, sorry, 5 by 2 I can write here, 5 by 2, okay. So what we have here finally, 5 times that of mass of A. So uncertainty in the velocities, okay, the ratio of 5 times the mass of A, what is the uncertainty in their position. So we have the mass of B is 5 times the mass of A, so 5, 2 here we have, and ratio of uncertainties will be 25 by 2 we got now. Mass of B,
Mass of B is 0.2 na sir.
where do we have, 1 minute, the uncertainty in the velocities, okay, cities of A is, mass of A is, area, see here, mass of, okay, so what is the mass of B given?
0.02.
See, mass of B is given as 5 times the mass of A, so I can write 5 times of Ma, and here Ma, okay. Next, what about velocity of B given? See, the uncertainty in the velocity of A is how much? 0.05. So uncertainty in velocity of A is 0.05. And what is the uncertainty in velocity of B? 0.02. Okay. So here 5, this will be 0.01 time. So what we got here? 2. So simple now. So what is our answer here? 2. So 2 will be your answer here. Is this clear or not? Just simple formula substitution only. Okay, this is level 1 model questions. Okay, both this one and the previous one here. So if you haven't noted that, just note this first. Yeah, so after this I will be showing few more questions. Just take them as homework and just give a try for them. Over? Yeah. So just look at this JEE mains question. An accelerated electron has a speed of 5 into 10 power 6 meter per second with an uncertainty 0.02. Okay. The uncertainty in the finding its location, while in the motion is x into 10 power minus 9 meter, the value of x. So what you will do here? See what we have, delta p and delta x will be h by 4 pi you can use. So what they given data here? Speed, velocity is given this much, has velocity with uncertainty this much. So it means delta v should be taken as 5 into 10 power 6, and what is the error here? Uncertainty, and it means 0.02 by 100. Okay, so it will be 5 into, so I can remove this 10 power 4, okay, and you can write this as 10 power minus 2, it means 10 power 2 and here 2, so 10 into 10 power 2, okay, so it will be 10 power 3, this will be the delta v, okay. So substitute here delta x into m, delta v we have now h by 4 pi, okay. So now what they are asking?
X.
Delta x they are asking. What is the mass of electron?
Mass of electron is 9.
Everything is given, so substitute here, you will get this value. Okay, so take this and finish the work. Okay, yeah. Next we have to discuss about quantum numbers if you are done with this question first.
Which is equals to 6.63 into 10 to the power minus 34 to the second pi is equal to 3.14. Delta x is equals to what is 9.1 into 10 to the power
Over
minus 31. Delta v nothing but 10 to the power of 3 is equal to h by 6.6.
okay. So here we have quantum numbers. What is the use of these quantum numbers here? See, we know, for example, if I want to mention the address of a particular person, so how we are expressing? We are saying from where, which country he is, and which city he is, and which area, I mean which city and which area, and his house number. Like this, we are specifying everything now. So for electron also, in which orbital it is, it means which shell it is. Okay, it means in order to express this shell number, we have principal quantum number. Again, in which orbital we are saying, again we are saying it as subshell first. Okay, which is given by angular momentum quantum number, which is indicated with L. Okay, like that we have different quantum numbers, like 4 are there. So first 3 quantum number is, first 3 are what? Principal quantum number, which is indicated with symbol N, and another one is azimuthal quantum number indicated with L, and another one is angular moment, like angular quantum number M or ML, and final one is MS or simply S, spin quantum number. So these first 3 comes from Schrodinger wave equation, by solving Schrodinger wave equation. Okay, so this comes like this is added separately, but these are the 3 quantum numbers comes from Schrodinger wave equation. Okay, so these are a set of 4 quantum numbers with the help of which we can get complete information about what? About all the electrons in an atom, something like location, energy, and type of orbital occupied, and what is the shape of orbital, and what is the orientation of that particular electron. Okay, so what are the 4 quantum numbers? Principal quantum number, azimuthal quantum number, magnetic quantum number, and next spin quantum numbers. Okay, these set of 4 quantum numbers required to define an electron completely. So first one, what we have? Principal. So it tells us about energy. Okay, so it tells us about what? Energy, and to which the electron is belongs to. Like we are representing now, even in the Bohr model also we have studied like 1, 2, 3 like that, like numbers. Okay, orbital numbers. So here like 1, 2, 3 so on we are taking. As n value increases, what happens to the energy? Energy also increases, which we have seen with the help of that energies, like this we have taken. So as n value increases, energy also increases, but energy gap decreases, I have discussed. Okay, so if n value increases, what happens to the energy? Increases. Okay, so now the energy, for example, I have 2 types of systems here. One is single electron system, means hydrogen like system. It means hydrogen atom contains how many electrons? Like single electron system it is hydrogen or hydrogen like system, like hydrogen or helium plus or lithium plus 2, like this means these are single electron systems. And we have multi electron system like carbon, nitrogen we are writing now. So in this case we have different energies. It means what I told you, principal quantum number decides the energy order or energy of that electron in which that electron is present, we have discussed now. So we have orbitals like 1s, 2s, 2p, next 1s, 2s, 2p, and next 3s, 3p, 3d, like this we have. Okay, now they will ask what is the energy order. For single electron system, you just consider n value. What I am saying? Consider n value. Higher the n, greater will be the energy. So here 1s, 2s, which is having higher energy? 2s. And 2s, 2p? 2p. Now what I told you, just consider n value. So which is having n value, both of them have same now. So these are degenerate orbitals. Okay, 2s equals to 2p. And next here equal. So these 3 are degenerate. It means what? Same energy shells. Okay, they have same energies. when it comes to the multi-electron system, so here energy depends on both n plus L value. So it is depending on what? N plus L value. Okay, so this L value comes from what? The subsidiary quantum number, that is what? Azimuthal quantum number. Okay, so for s orbital L value will be different, p orbital will be different, d will be different. So here itself I just want to add it here. So if L equals to 0, I should say the orbital will be, the subshell will be s. So what is the L value for s subshell? 0. For p subshell 1. For d 2. For f, see, like this we have. Okay, so now what we can consider? N plus L. So if I write 1s, 2s, 3s, like 2s, 2p if I write, these things I am writing. Now tell me their energy orders. Which is having greater energy? See, n plus L value you should take now. So what is the n value? 2. P has 1. So this is 3. Here what about this? 2 plus 0. So higher the n plus L value, greater is the energy. So I should write it like this. Is that clear or not? Both scenarios are different.
Yes.
Okay, yeah. Just make a note of this. कुछ नहीं. Yeah, is that clear now? So what we discussed, for single electron system it depends only on n value, for multi it will be n plus L. Okay, so maximum, see, now look at here, maximum number of subshells present will be taken as n square. Okay, for example, here I'm showing here. So for s orbital, for s subshell we have only one orbital that comes from L values, I will tell you. So now 2s, 2p are degenerate states we are seeing. Okay, so what is the n value here? We have 2 right now. So you just take n square, so that we will get number of orbitals present in that particular n value. In a particular shell, how many orbitals are present comes from its n value. Just take n square. Okay, for example, here I am saying 2 now, so 2 square means 4, that is 1 is 2s and remaining 3 are 2p's. I mean, how it will be? 2px, 2py, 2pz. So like this, total orbitals are how many we have now? 1, 2, 3, 4. Okay, like that you need to calculate. Okay, now each orbital can accommodate how many electrons? It can accommodate 2 electrons. So maximum number of electrons possible in an nth shell means 2 into n square. 2 into n square. In an energy level, nth energy level, maximum electrons possible means you should say 2n square. Okay, so like 4 into 2 means 8 only. It is correct only here, no worries. Okay, and now I am asking, maximum electrons that can be filled in orbital means 2. In the shell means you use this formula. Okay. Okay. So next, what is the second one we have? So it is a subsidiary quantum number. After n, we need to look for the L value. Okay. So it is also known as subsidiary quantum number, and it tells about the number of subshells present in an energy level. Okay. Angular quantum number of an electron present in a subshell, like it says about shapes of various subshells. Like shapes means s orbital has spherical in shape and p has dumbbell shape. Okay, again d double dumbbell, like that. So for s, what is the L value? I told you 0, and for p 1, for d 2, like that you should write. Okay, so now See, for a particular n value, L will be always lesser than n. Okay, always less. For example, n equals to 2 I am writing. What are the possible L values we can write? 1, 0, comma 1. For a particular n value 3, so it can be, L can be 0, 1, 2. Okay, it means 0 means which orbital, which subshell it is? L0 means what is that? S subshell. Okay, and L1 means P subshell. So now in the second energy shell or second energy level, so do we have d orbital? No. What I am saying, at second energy level n equals to 2, do we have d? No. Why? Because L value cannot be equals to or greater than 2. It's always less than 2. I mean less than that n value. Okay. So for a particular n value, n equals to 3 I am saying. What are the possible L values you are saying? 0, 1, 2. So 0, 1, 2 means what are the possible orbitals or possible subshells we have? S, P, D. Right now? S, 0, 1, 2. So S, P, D we are writing. So what I should write this as? 3S, 3P, 3D we are writing. So now they will ask, what about their energy order in the case of single electron, or they will mention hydrogen atom case, and in the case of multi-electron. So what is your order for their energies? Single electron case? What we need to consider in the case of single electron? Only L values we should consider. All of them have same now, so all of them are with equal energies, like this. In case of multi-electron, L plus L. What is the n value here? 3. L value 0. So this is just 3, and this one 3 plus 1, 4, 5. So 3D greater 3P, 3S. Is this clear or not? Is this clear or not? Clear or not? This one? Yeah. Next thing. Next we have magnetic quantum numbers. So this gives information about spatial orientation of orbitals with respect to the standard coordinate axis. Okay. For example, for a possible n value, what we discussed, L will be always less than n. So for possible L value now, we have ML values ranging from minus L to plus L. Okay. So what are the values we can possible for, if I say L equals to some 2, what are the ML values we have? What are the orientations we can get? Minus 2, next 0, plus 1, plus 2. So total values how many we got? 5. Okay. So you can use 2L plus 1, number of orbitals possible for a particular L value is 2L plus 1. Okay. So for example, what is the L value for P?
1.
P is 1 right now. So what number of orbitals possible will be? 2L plus 1 I am saying. L value is 1 plus 1. So 3. So you are saying minus 1, 0, plus 1. So that's why we are writing a 3 boxes here. Each box represent 1 orbital. Okay. Is that clear or not? Yeah. So for a particular, see, for S subshell, what is the L value? 0. So number of orbitals will be 1. For a P subshell, it will be L equals to 1, means these are the 3 orbitals. For D, 2. So 2 into 2 plus 1, 5 now. So these are the 5 possible orbitals we have. Okay. For F subshell, L equals to 3. So 2, 3 is a 6 plus 1. So 7 orbitals are possible with these values ranging from minus 3 to plus 3. Okay. So now maximum number of electrons filled in F orbital.
14.
What is my question? maximum number of electrons filled in f orbital.
14.
Orbital na, so it should be 2 only. Whenever the word orbital is there, it should be 2.
Orbital.
So now maximum number of electrons filled in f subshell, if I ask, f subshell 14. Is that difference, is that clear? Yeah. So there is a question like this in the previous case, like orbital they mentioned, blender they will do, it will be 14 or some 10, something like that they will do. So it will not be, yeah, energies we have written. Next, spin quantum number. This explains as what? Spin or the orientation of electron. For example, around the nucleus we know electron has a spin right now. So here you can see electron in an atom not only spins around the nucleus, but it has its own
Axis.
it will like have its own spin axis. Okay, so that spin can be either clockwise or anti-clockwise. If you represent one spin as clockwise, means if you represent it as plus half, then the opposite spin be minus half, or you can take in opposite manner also. If this is minus half, this should be plus half, like that. Okay, yeah, but both of them should have opposite spin. Okay, so that's it. So now what is the use of this? It explains or it helps us to find magnetic properties of substance. For example, in any atom or any substance have some unpaired electrons are present. If it contains unpaired electrons, then you can say it as paramagnetic. If no unpaired electron, no unpaired electrons, you can say diamagnetic. Right now, diamagnetic. Okay, so now, so tell me, here I am giving a substance have d5 electrons. How can we fill this? How many d orbitals we have? 2l plus 1, d l equals to 2 means 2 to the 4 plus 1, 5 now. So 5 boxes you put like this. Okay, each box represent one orbital. Okay, 5 electrons are there, now fill. 1 like this you fill. What is the total spin we will get here? Total spin means 5 are there, each one is having plus half. So you can say 5 by 2 total spin if they ask. Okay, and if they ask for magnetic moment, the spin only magnetic moment value is what? Root over n into n plus 2 Bohr magnetons, you can say. Okay, what is the n value? N represents here number of unpaired electrons. How many are there? 5 are there. So 5 into 5 plus 2, 7 Bohr magnetons. So root 35 means this is around root 36 is 6. So root 35 around same value, no? So like 5.85 around the value you will get Bohr magnetons like this. Okay, now if I say d6, how many unpaired electrons are there?
4.
d6, first 5 fill like this, next pair up will be taking place. So n value should be 4. So root over 4 into 4 plus 2 means root 24. Okay, so like that you will be getting the values. Is that clear? Yeah. Next, yeah, I will show you 1 or 2 questions last. So tell me, what is the energy of these orbitals? I mean, whatever the answers you can give it. The quantum numbers for 4 electrons are given below. Decreasing order of energies of these electrons. Which is having higher energy, tell me first. Fast. Huh? N equals to 4. See, whenever they have been mentioned single electron, always consider that is for multi-electron system. So energy for multi-electron system is considered from n plus L value. So consider which is having higher n plus L value. First consider n plus L value. This is 6 first case, and this is 5, and this is 5, and this is 4. So which is having greater n plus L? First one. So 1 greater, after that these are having, both of them having same energy. So what to consider here?
L value.
So if n plus L value are same, consider greater the n value, greater is the energy. These are the 2 steps. Okay, so this one, so 1, 3, 2, 4. We have now 1, 3, 2, 4. So second option will be your answer. Is that clear? Right. So one last question for practice purpose. You can do this, and remaining questions you can practice on your own. If any questions are there, we will discuss in the next class. Just tell me answer for this. This previous question.
4D, 5B, 5, 6. Orbitals are in order descending in
Fast.
descending vectors.
Okay. Tell me fast. This one last answer. You tell me and go.
4,000.
So just find.